Exam 4, question number 19. Suppose that x1 through x5 is a random sample from a distribution with density function f of x equal to 1 over theta, where x is between 0 and theta. The null hypothesis that theta is equal to 1 is to be tested against the alternative hypothesis that theta is equal to 2, so that the significance level is alpha is exactly 1 over 32. The null hypothesis, H naught, is rejected if the maximum xi is greater than c. What is the appropriate value of c? Okay, here we're given a null hypothesis, an alternative hypothesis, and the problem tells us that the rejection region is that the largest value of x greater than c is the rejection region. What's the appropriate value of c? Well, that we get into order statistics again, and under the null hypothesis that theta is 1, the fifth order statistic, this is the distribution. And again, this is order statistics is something that just you're going to have to know and learn, and once you learn it, then it becomes very straightforward to find the density of any order statistic and enjoy order statistics. So then to find the value of c, so being greater than c, so c from c to 1, we know it equals 1/32. And here's our density. So we integrate, x to the fifth, plug in our values. It implies that c to the fifth is this. Take the fifth root to both sides, and we get the 31 raised to the 1/5 over 2. Number 20. Suppose x is a random variable with probability that x equal to 1 is p, and the probability that x equal to k plus 1 is equal to 1 minus p times the probability that x is equal to k. And this is for k equal to 1, 2, all the way to infinity, and p is between 0 and 1. What is the expected value of x? Now, problem 20 is a fun problem to me. And there's 4 different ways to do this, and I think each has their own merit. And I'm going to go through all 4 of these. If you've seen one of these derivations and not the others, then we've done a good thing here. Now, let's ignore this first line for a second. The problem tells us the probability that x is equal to 1 is p, and then it gives a crazy relationship that boils down to if it's 2, then it's this probability. If it's 3, it's this probability, and you keep going. So this is a general formula for the problem that is given, okay? And that's for x equal 1, 2, 3, etc. So one of the ways to do it is to, and whenever you're going to take expected values, and that's what the problem asks us, is what's the expected value of x, is let's look at the general negative binomial. And this is one of 2 ways that it's usually written, and the next solution will use the other way, where x is the number of trials beyond r, which is we're looking for r successes. Okay, in our problem it's 1, but this is the general negative binomial, and so x goes from 0 to 1. And we know that the sum of this over all values is 1 because it's a probability mass function. Okay, so whenever we take the expected value of stuff, we want to trick it to look like another density or probability mass function, and then we know that integrates to 1 and things simplify. So that's what we're going to do here. We need to find the expected value of x. Okay. So remember, we're under this, according to the problem, this is our f of x, or probability mass function. And but we're summing from I equals 1 to infinity. So we put in the value, and then times the probability of that value is this. Okay, so let's keep this piece the same, but we're gonna trick this I. So if we do combinatorics, I choose I minus 1 ways right here, well, we get I back. And so this, from here to here, nothing has changed. But now we're going to do a change of variable. We're going to let y equal to I minus 1. So right here will be y. This will be y. I is y plus 1. And then instead of going from I equal 1 to infinity, we're going to go from y equal to 0 to infinity. And that's what we get here. So this is just a simple substitution. Remember, what we plug in for the variable for our summation is sort of a dummy variable, so it doesn't matter. But what we've done, what I want to do here is I want to trick this into being a general formula. So if we divide by p and multiply by p, so that makes this p squared, and you know that, and the p's out front that doesn't count in the summation, then we basically add 1 and subtract 1 to the top, and then the y stays the same. This is the general formula for a general negative binomial when r is 2. And we know this sums to 1, so the answer is 1 over p. Okay? Now, let's do it another way. Here, the negative binomial, x is the number of trials to get r successes. So here, we know we have to have at least r trials because we have to have at least r successes, which is what p represents. And so this is another way to express the general negative binomial. So what we do is we look at the expected value of x, which is this, which we saw before. Now let's do a substitution that y minus 2 is equal to I minus 1. And so y minus 2 would go here, and then an I, well, let's just look at it. Then using the combinatorics, it would simplify to this, and we're going to do the same thing. We multiply by p and divide by p, so that's how we get the p squared. And then this right here is the general formula when r is equal to 2. So this piece right here sums to 1, leaving 1 over p. So that's another solution. And those are pretty common to trick it into looking like another negative binomial. So now this is more of a direct approach here. So if we let this expected value of x is this, we know that from the previous two solutions. But let's write this out a few terms just to make it easier what I'm going to do next. And so you take 1, you go from 1 and 1 here, which makes that 0, and then I equal 2 and 3 and etc. And it goes to infinity. Now, if we take this sum, which equals this, and multiply it through by p, or 1 minus p, okay? So then we get 1 minus p expected value of x. So here, since there's 0, but we're multiplying through by 1 of those, so there's 1. And then wherever we just basically increment the exponent by 1 each time, because we multiplied through by a y minus p. Now let's take this equation minus this equation. Okay, so here we'll just, let's look at it. So this piece is here. Now this piece, so they has a 1 minus p to the first p, that's this term and this term. So this term, there's 2 of them, minus 1, there's 1 left. And here the squared term, 3, 1 minus p squared p, and there's only 2 of those here. So this minus this, there's 1. And then you keep going, and it's good, and the next term is going to be 1 minus p cubed times p, and etc. Well, this side looks sort of like a geometric series if we factor out a p. So let's, and this side, when you multiply that in here and subtract, you get p times expected value of x. And then what we do is we factor out a p, and then what's left is this sum, and this is less than 1, so it's a geometric series, 1 over 1 minus, and then this value. Well, this becomes 1 over p, and p times 1 over p is just 1, but 1 is equal to p times expected value of x, so that implies the expected value is 1 over p, the same solution that we got in the previous two problems, two solutions. So here is a fourth solution and final solution. We know that this geometric series is equal to 1 over p, and we just showed that this piece was this that simplified to 1 over p, so that's here. And it's just a geometric series. So if we take the derivative of both sides, and remember this goes from 0 to infinity, just like this. So if we take the derivative of here, so it's I out front, and then 1 minus 1 of these, and then times the chain rule, the derivative of p, you get minus 1. And the derivative of this is going to be minus 1 over p squared. Okay. Well, the first term, I equals 0, really doesn't play a part because it's just 0. So we can change that to 1, I equal 1. And this negative and that negative, we can multiply through by negative, and those go away. And then we can multiply by p to both sides. So one of the p's goes away, and we get a p here. Well, now this is looking very similar to what we want to find out. That's the expected value of x in our problem, which is 1 over p. Number 21. 5 urns are numbered 3, 4, 5, 6, and 7 respectively. Inside each urn is n squared dollars, where n is the number on the urn. The following experiment is performed. An urn is selected at random. If its number is a prime number, the experimenter receives the amount in the urn, and the experiment is over. If it is a number that is not a prime number, a second urn is selected from the remaining 4, and the experimenter receives the total amount in the 2 urns selected. What is the probability that the experimenter ends up with exactly $25? Now, problem number 21, we want to find the probability that we end up with exactly $25. So if we choose the 5th urn, it's prime, we get n squared, so we get $25. So then we stop because it's prime, we get 25. So that's the solution. And the only other way to get $25 is if we choose the 4th urn on the first pick, and on the second pick, the 3rd urn. So then these, we'd get 16 and 9, which is 25. So that's another way. But this is equal to, well, that just carries over, and then this is like an intersection, so it's x1 intersecting x2, so that changes to the probability of x1 times the probability of x2 given x1. Well, we know these, that's 1/5. Probably that we have just flat out picked the 4th one is 1/5. And then given that we've chosen the 4th one, that's eliminated, then we picked a 3rd one, it's just 1 over 4. So add those together, you get 1/4. Number 22, let x have a distribution with the 75 percentile equal to 1/3 and the density function equal to f of x, which is lambda e to the minus lambda x for x positive. What is lambda? So here we're given that the The 75th quantile is 1/3. So by definition, this is what is given. Well, we're also given that this is the density. So going from 0 to 1/3 is what this says is equal to 0.75. Well, let's integrate this. If we do a U substitution, we get this, integrate it, and then bring it back to the X world, take it, plug in its limits, we get 3/4. Now 3/4, it's 3/4 because that's what they tell us. It's 75%, this probability. Well, now this relationship, if we take that over and bring this over, we get that it equals 1/4. Now we take the natural log of both sides, and then the 4 can be brought up to 4 to the -1, and then when you take the log, it comes out front, and then we can multiply through by a negative, and that goes away, and then we multiply by 3 to just leave the lambda, but we can take the 3 as an exponent and make it 64. So this lambda is equal to the log of 64. Number 23, given theta, the random variable x has a binomial distribution with n equal to and the probability of success theta. If the prior density of theta is f of x equal to k for theta between 1/2 and 1 and 0 otherwise, what is the Bayes estimate of theta for squared error loss if x equal 1? So number 23, I'm not going to have room to put it on there. So here, this is where it's we want to find the Bayes estimate under squared loss. And so this is squared loss. So we want to find an estimate delta for our parameter theta under squared loss. And what that means is it's the expected value of our loss function given our data, in the Bayes world. Well, we can multiply this out and then bring the expectation through. So we get theta squared, which is this, and then we get -2 delta theta squared, and then these are constants, so they come out, and then we left with delta squared, which is a constant. So the expected value of a constant is just a constant, so we get this. Now, we want to minimize this function for all delta. That's the goal. We're going to make this bigger, make it smaller until we find the minimum of this. Well, to find the minimum, we take the derivative with respect to delta. So let's take the derivative of this with respect to delta, and then this is a constant. So here we get -2 expected value of x plus 2 delta, set it equal to 0. Then our delta is the expected value of theta given x. So we need to find the mean of using our what's called a posterior distribution. So now let's start plugging in and finding the distribution. So here, the expected value of theta given x. So we need to find f of theta given x and then find the mean of it. So here is theta given x, and then since that's a conditional, we can write it as the joint divided by f of x. And initially I just put f, 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 but really they're different f's. So then I put subscript 1, 2, and 3, and 4 to make sure to illustrate they're technically different functions. Well, then this joint can be rewritten as f4 of x given theta times the prior of theta. And then we're given this, and we're given this, it's binomial. And this piece we're going to have to calculate. And the f of 3x is we integrate over actually this top part here, d theta, integrate out theta, and that leaves just fx. Now there's shortcuts here that we could technically do this, integrate it, find the constant that makes it 1, but we'll just kind of use the crank and grind method here. So We're also given that x equal 1, which helps, it simplifies the problem. So f3 of x equal 1, and here we're given that this is a binomial of n equal 2 and the probability parameter is theta, and this is easy to figure out. They call it k, but you have to find the value that makes it 1, which is 2. So we integrate from 1/2 to 1, which is our domain for theta. So this is the binomial, 2 choose 1, because we're given x is 1. Theta the first, 1 minus theta to the 2 minus 1, which is 1, and then the 2 is our prior distribution, and then that equals this when you integrate. So this is 2 and this 2, which is 4, and then this is theta squared over 1/2, which then reduce the 1/2 and the 4 cancel anyway, and then we get this, and so it's 1/3. So now we want to find this the full density, and we're given all these pieces now. We've found this, we're given that, we're given this. So f of theta given 1 is well, we have the binomial piece here, and then the prior, and then the f of 3, which is 1/3, and then this simplifies to 12 theta 1 minus theta. So to find the expected value for this function, which is this piece, then you have to plug in a theta times this distribution, this density. So we take theta times 12 times theta 1 minus theta, so the theta becomes squared. Well, then when you integrate this, you get this, you plug in the values, and you get 11/16 as an answer. Number 24, a statistical procedure has been designed to test the null hypothesis that theta is equal to 0 against the alternative hypothesis that theta is equal to 1 as significance level of alpha. If the same procedure is used to test the same null hypothesis against the composite alternative that theta is greater than 0, then the significance level will... So number 24 is short and sweet. So it wants to know, will the rejection region change if you use a simple alternative versus a composite? And the answer is no, because the rejection region is determined by this statement here. Alpha equals probability to reject the null given that the null is true. And so the alternative doesn't play a part of this, so it won't change. The answer is A. Number 25. A continuous random variable x has a density function f of x as shown below. What is the probability that x is between 0 and 1? So number 25, we're given this graph here, and this is our function. So we have to find the value of k. And we do that the area here and here have to add to 1. So the area must be 1. So the area of the left triangle is 1/2 8k. Remember, we're talking distance, so that's a positive value. And then times the height of 0.1. Plus the triangle on the right is 1/2 times the base times the height, boils down to k equal 2. And then if you wanted to, you could find the value of each of these equations, and you could do that by rise over run, you know, the rise over the run, and it boils down to this, but it's really not needed because we want to know the probability that x between 0 and 1, which is in this triangle, k is 2, so to be less than 1 is this little triangle here. So that area ends up being the probability. So the area of a triangle is 1/2 times the base, remember, and we want between 0 and 1, and the height. Well, this is the function evaluated at 1, which is 1/10. So we get, the answer is 1/20. Number 26, suppose one wants to test that the numbers 0, 1, 1, 2, 2, 3, 3, 3, 3, 3 are the ordered values of 10 independent observations from a binomial distribution with n equal 3 and p equal to a half. What is the chi-square goodness of fit statistic, and when would the binomial model with p equal to 1/2 be rejected at the significance level of alpha equal to 0.05 respectively? So problem 26, this is a classic chi-square test. So we want to know, these are our values, 0, 1, 2, and 3. And we want to know, is it a true binomial? Well, we conduct an experiment of 10 samples and we get 1 0 and 2 1s and 2 2s and 5 3s. Well, if this were a true binomial of 1/2, then the probability that we observe a 0 is 1/8. So actually this should not be xi. This is the probability of observing this this value. Maybe this should be O for outcome, and that's x. So the probability that we observe a 1 is 3/8, assuming that it's probability is 1/2. So the probability we observe 2 is 3/8. Probability we observe a 3 is 1/8. And then the expected value is, well, we've done 10 observations and 1/8 of them should be in here. So 10 times 1/8 is 5/4. And we would expect 3/8 of the 10 observations to be here, which is 15/4. Same for here, and then 1/8 of them, 15/4. So the chi-square test is we sum over each of these categories, taking the observed minus its expected, square it, divided by its expected. And then in this setting is the expected is n, which is the number of trials we did, which is 10, times the probability of observing that event, which are these cases here. So we write out the sum, using this formula, and that all boils down to 194/15. And the rejection region with 1, 2, 3, 4, so it's k minus 1, so it's 3 degrees of freedom. We want the right tail area of 0.05. We look in the chi-square table and the critical value is 7.82.